We talk a lot about how intelligent large language models are, right? Their ability to write prose, complex code, synthesize information. It's all very impressive.
It is.
But there's this persistent structural limit that plagues even the best models out there.
The reliability problem.
Exactly. Their fundamental inability to execute long-range tasks reliably.
It's really the Achilles heel of scaling AI. I mean, think about it. If you have an LLM that's 99% accurate on a single step, that sounds fantastic.
That sounds great to me.
But it's disastrous when you chain those steps together. If you need, say, 100 perfect steps in a row, that 1% error rate pretty much guarantees failure.
The probability just collapses.
It plunges exponentially towards zero, and it happens fast. We are hitting a ceiling in how we can use these really powerful tools for complex real-world jobs.
And this is why the study we're diving into today represents such a monumental shift. They took on the ultimate endurance test,
The 20-disk Towers of Hanoi.
which required the system to execute over 1 million sequential LLM operations, 1,048,575 steps to be precise.
And here's the part that just blows my mind. The system, using this maker framework, that's maximal agentic decomposition, error correction, and red flagging, it solved it with 0 errors.
Zero. Over 1 million steps.
Yeah, and this wasn't done by just making the base model a little bit smarter. This is a completely orthogonal approach to scaling AI. We're not just building bigger monolithic models, we are fundamentally restructuring the entire process.
So our mission today is a deep dive into the mathematical and conceptual rigor of this new architecture, what they call massively decomposed agentic processes, or MDAPs. We really want to get into the math and show you exactly how they dodged that exponential failure cliff.
Let's start by grounding this reliability crisis in the real world. Just think about any massive technological achievement. A skyscraper needs millions of structural checks, right?
Or a modern hospital.
A modern hospital, a complex manufacturing line. These things require billions of precise steps, countless layers of perfectly executed protocols.
Exactly. And when you try to use LLMs for planning or execution in those kinds of environments, that 1% per step error rate, which might look good on some academic benchmark,
It becomes catastrophic.
you're talking about massive financial loss or even physical harm. You just can't afford that kind of cascading failure.
And that's why Towers of Hanoi is such a perfect, almost brutal test bed for this.
Yeah.
It's conceptually simple, but the difficulty scales exponentially. It's 2 to the power of d minus 1 steps.
So it gets out of hand really, really fast.
So fast. And when researchers tested state-of-the-art monolithic LLMs on it, the results were completely consistent. They all failed. And they failed almost immediately, usually after just 5 or 6 disks.
It confirms the core problem. The longer the task, the more the performance deteriorates. Chained reasoning in a single large context is just inherently unreliable.
It's a hard wall of exponential failure.
So, if that monolithic approach is doomed, this maker framework flips the script entirely. It's all about modularity and rigor. So, tell us how this massively decomposed agentic process concept structurally tackles this problem.
The insight really comes from computer science and even biology. It's about designing for failure and using massive redundancy. So instead of one large, brittle agent handling everything, you shatter the task into its smallest possible components, and then you have specialized microagents manage each tiny piece. This structure is what lets you apply these really powerful error correction mechanisms.
That makes so much sense, and it immediately brings to mind that biological analogy they used in the source material. Cancer resistance in elephants, yeah.
That's right. Elephants, just because of their size and their lifespan, statistically they should have far higher cancer rates than they do, but they don't.
And the theory is?
The research suggests it's because of redundant systems right at the cellular level that detect and suppress failures cancer early on. And MDAPs mimic this. Instead of relying on one superagent to never make a single mistake, you rely on massive local error correction to make sure the whole task moves forward reliably.
Okay, let's break down the 3 core components of Maker. Let's start with the foundation, maximal agentic decomposition, or M.
So AMD is this really extreme principle of reductionism. You decompose the entire task to the minimum possible granularity. That means M equals 1 step per subtask.
But wait a second. If the goal is 1 million steps, doesn't breaking it into 1 million individual microtasks just create, well, 1 million points of potential failure? It sounds wildly inefficient. Why is that maximal granularity so important?
That's a crucial question, and the answer is all about context management and cost. By strictly limiting the context for each microagent to only what's required for that single step, you drastically reduce the chance of confusion.
Oh.
The LLM doesn't need to hold the entire history of the puzzle in its prompt. It just needs to know, move disk 1 from peg A to peg C.
So the task becomes super simple for that one agent.
It makes the task achievable, improves the base error rate, and critically, it lets you use smaller, cheaper models like GPT 4.1-mini. But you're right, it does create a million potential failure points, which brings us to the mathematical solution.
The necessary countermeasure. Component 2, which is error correction, handled through this first to ahead by K voting.
Right. Since modularity enables correction, you can turn the problem of failure into a statistical certainty of success. For each tiny subtask, the system just draws candidate samples until one candidate move is K times ahead of any other in the votes.
And it stops as soon as it hits that margin K.
The moment it hits it. This method is inspired by the sequential probability ratio test, or SPRT.
So for listeners who, maybe aren't deep into statistical sampling, how should we think about SPRT? Conceptually, I mean.
You can think of it like a rapid confidence check. So instead of running a fixed number of tests, say 10 samples every single time, SPRT is the optimal way to decide when you've collected just enough evidence to be confident without wasting compute on redundant data.
So it's efficient.
Extremely efficient. If the correct answer has a base success probability, let's call it P, that's greater than half, then by increasing the margin K, you can push the probability that the correct outcome wins to basically 1. You practically eliminate the error for that single step.
And before the voting even starts, there's a quality control layer. Component 3, red flagging. This weeds out the bad actors.
Precisely. The research found that bad outputs from LLMs often show predictable pathologies. So if a response signals some kind of pathological behavior, it gets flagged and just discarded before it can even be counted as a vote.
It's a filter.
It's a filter that increases your per-step success rate, PP, before the voting even kicks in. The key flags they found were, for example, overly long responses, which correlated with confusion, where the model starts rambling instead of just stating the move and incorrectly formatted responses. Discarding those is vital to mitigate correlated errors.
Okay, that gives us the conceptual overview. Now let's shift to the mathematical core of this system, because this is where I think the genius of Maker really shines. This is the part we wanted to do a deep dive on. It's the mathematics that guarantees this thing can scale.
This is the crux of it. We need a formal understanding of how reliability and cost scale with the task size, which we'll call S. And the math confirms that the probability of full success across the entire task, P-full, can be rigorously maintained just by increasing that confidence margin, Cal.
And the mathematical insight here is just staggering, especially when you compare it to the exponential failure they started with.
It really is. If S is the total number of steps, so over 1 million for Hanoi, the key finding, which is formalized in their equation 14, is that the minimum required vote margin, KNS, grows only logarithmically with S.
So K-min is theta of log S.
Exactly. Theta LNS.
So we've gone from an exponential growth of failure to a logarithmic growth in the effort needed to stay perfect. For those of us who appreciate the math, why is logarithmic scaling, that theta of log S, so incredibly efficient?
Well, exponential growth, which is what you face with monolithic models, it shoots up like a vertical wall. It's uncontrollable. Logarithmic growth, on the other hand, is almost flat.
Right.
Think of it this way. To maintain reliability over, say, 1,000 steps might require a margin of K equals 3. If you scale that task up by a factor of 1,000 to 1 million steps, the margin 8 might only need to increase to, say, 4 or 5.
That's it, just a tiny increase.
That slight logarithmic increase in verification effort is enough to mathematically guarantee the system's success over a vastly larger scale. That stability is the key.
Okay, that logarithmic stability handles reliability. But you still have to pay for all those votes. We could be talking about millions of API calls. How does the cost side of this equation stay manageable?
This is where the math, specifically their equation 17, gives the ultimate justification for maximal agentic decomposition. The analysis shows that if you try to make your microagents handle M steps, where M is greater than 1, even just 2 steps,
the cost grows exponentially with M.
Exactly, it explodes.
But why? Why does trying to make the agents just a little smarter, handle 2 steps instead of 1, cause such a devastating cost penalty?
Because the verification cost goes through the roof.
Yeah.
You're asking the voters to perfectly match a sequence of decisions across multiple parallel samples. The probability of getting 2 or 3 steps right in a row in the exact same sequence across all your samples, it vanishes incredibly quickly.
So the voting system just has to keep sampling and sampling.
Thousands of times just to hit the margin K. It makes any kind of non-maximal decomposition totally impractical, cost prohibitive instantly.
So MAD, M equals 1, isn't just a strategic choice. It's a mathematical necessity for this to be cost-effective.
Precisely. By sticking to MAD, the system gets this highly efficient scaling pattern from equation 18. The expected cost is proportional to theta of S log S.
Log linear.
Log linear scaling. That is the gold standard for efficient algorithms in classical computing. Think about merge, sort, things like that. It means the time cost of the task scales only linearly with S if you can parallelize it, which is why they can tackle 1 million steps without waiting for years.
And this rigor even drove their model selection. They didn't just pick the LLM with the lowest error rate.
No, they picked the one that minimized cost over success rate. The scaling law let them create a formal optimization strategy. Minimize the ratio of C over P. And their empirical data showed that GPT 4.1 mini, run at a low temperature, was actually the most cost-effective chase for the 20-disk task.
Even though other models might have had a slightly better inherent error rate.
Right. This predictive power saved them a massive amount in experimental costs.
Okay, so the theory is airtight. The math guarantees stability. Let's talk about the proof. The successful solution of the 20-disk Towers of Hanoi, over 1 million steps, 0 errors, using GPT 4.1 mini and a margin of K equals 3. That is a major milestone.
It's the ultimate validation. A 0-error execution over 1 million steps with a relatively small, cheap LLM is a huge technological feat. But the most instructive part is how the system converged.
Right. I found the data on the steep exponential decay of undecided steps to be really telling.
That phrase is so important. It means the vast majority of the steps reached that required confidence margin of K equals 3 almost immediately. After the first few sampling rounds, the number of steps that still needed more voting just dropped off a cliff.
It followed an exponential decay curve.
Exactly. So practically speaking, even though they could have gone to thousands of votes to resolve a tough step, most steps were resolved instantly with just 3 calls.
So the extra cost for those tricky steps is basically negligible in the grand scheme of things.
It becomes a computational rounding error, because their base success rate, P, was high enough that convergence was near instantaneous for almost all of the subtasks.
Let's circle back to red flagging for a moment. What role did that play in dealing with correlated errors?
Correlated errors are the killer in these long horizon tasks. A single confusing input can cause the LLM to get stuck in a kind of pathological loop, making the same mistake across multiple parallel samples.
Which would trick the voting system.
It would. But the research clearly showed the LLM error rate shot up once responses got longer than about 700 tokens. It was a clear signal the model was getting confused, trying to over-explain or add irrelevant context.
So by enforcing a simple, strict rule, just give the move, don't talk too much, they were able to cut out that systematic failure mode.
Precisely. Red flagging, by just discarding those verbose or badly formatted outputs, was instrumental in reducing collisions. That's steps where the first 2 votes were both incorrect. By cutting down on correlated errors, they ensured the votes were independent, which is the cornerstone for the math to hold up over 1 million steps.
Moving beyond this puzzle, the whole MDAP framework, it feels inherently familiar. It's almost like modern software architecture, but applied to AI.
It perfectly parallels the microservices architecture that underlies, modern cloud computing. You get modularity. Each microagent can be independently developed, scaled, updated. You design for failure, knowing the error correction can handle breakdowns.
And natural language becomes the API.
Natural language becomes this robust communication protocol between services, passing context from one single step agent to the next.
Now, the study focused on execution following a known strategy. The next frontier has to be applying this decomposition to LLM-based insights, where you need to generate the plan itself.
That's the recursive step, and they showed some really promising preliminary results applying a recursive version of Maker to large digit multiplication. That's incredibly taxing for standard transformers because of the long-range dependencies across the digits.
So in that setup, the system treats the creation of each subtask, the decomposition step itself, as a process that's also subject to voting and error correction.
So they're using Maker to generate the steps.
And then using Maker to verify the execution of those steps.
Exactly. This modular verified approach to inference allowed for reliable multi-step arithmetic. They got to 100% accuracy on 5 by 5 digit multiplication, which is a task where monolithic LLMs really struggle. It confirms the structural method applies not just to execution, but to planning and reasoning itself.
And finally, let's talk about the implications for AI safety. If we're scaling reliability and capability this way, through decomposition, not just bigger monolithic models, how does that change the risk profile of future AI?
It's a significantly positive development for safety and control. I mean, since each microagent has such a strictly limited focus and domain of influence, MDAPs inherently allow for better sandboxing, better auditing, and real-time control.
You can pinpoint exactly where an error happened.
You can. And this substantially reduces the risk of, say, colluding agents, or the unintentional, unpredictable emergence of harmful behaviors that people worry about with massive monolithic superintelligence. By achieving this huge scale through distributed, verifiable components, you get accountability.
That is a powerful and very practical conclusion. Scaling AI reliability doesn't require waiting for endlessly bigger, smarter monolithic models. It requires a structural shift to massive decomposition, all backed by the mathematical guarantee of log linear scaling and efficient error correction. We've traded guaranteed exponential failure for demonstrated zero-error execution over 1 million steps.
Indeed. It forces us to redefine what intelligence looks like at scale. It's not about monolithic brilliance, it's about structural soundness. So if extreme decomposition and mathematically efficient error correction are the keys to solving these huge problems, it raises a pretty important question for you, the listener.
What's that?
Given the demonstrated power of breaking tasks down, what real-world long-horizon problems at the level of organizations or maybe even complex societal governance might genuinely resist being broken down into small, reliably solvable microtasks? Where is the limit of decomposition?
Something to consider as you contemplate the structural architecture of the world around you. Thank you for joining us on this deep dive. We'll see you next time.